Good afternoon. Thank you, Jenny, for the very kind introduction. We have been friends for a very long time. And thank you very much to the organizing committee for inviting me, and in particular for Dr. Wu for all the hospitality that we have been shown every single time I have come to Taiwan. So thank you. I cannot only say thank you to the organizing committee because for some reason they put me after Professor Stocky. So I think this is the worst place to be when you're giving a talk after Professor Stocky, because I cannot be as entertaining, as interesting as Professor Stocky. So that's a fact. He always will tell you at the beginning of a presentation that he doesn't have much to show, and then he will talk about something that's extremely important. And we don't have nonlinear properties of rocks, so that is extremely important. So today I will talk about epistemic uncertainty in site response, and this follows directly from Professor Abrahamson's talk because he's talking about how we are characterizing, we are developing non-ergodic models, and one essential component of non-ergodic models is that you have to put back epistemic uncertainty. So when you're removing the you're removing uncertainty from the aleatory term, you have to put it on somehow you have to build back that epistemic uncertainty, and that's what this talk is about. So I will talk about the estimation of the site term and its epistemic uncertainty, uncertainty in the site effects estimation, and I will show some examples, or one example in particular from a recent project. So in the traditional approach for site response analysis, and here I'm talking about geotechnical practice in general, we take a profile and we place or find a location where we have an impedance contrast, when we get to a rock, and we apply input motion at that level, assuming that everything below that level is going to be an elastic half space. And then site response analysis are used to compute the motion that you get at the surface. We define amplification factors then as the spectral acceleration at the surface over the spectral acceleration of the input motion. The implicit assumptions, however, when you take this approach, is that the amplification factor is capturing site response with respect to an homogeneous half space. So you're making the assumption that you have an homogeneous half space, therefore you have no site effects that can result from any rock below the half space horizon. So if in reality you don't satisfy the assumptions of the half space horizon and there is an impedance contrast at depth, you're not capturing that in your site response analysis. There is also implicitly, the assumption is that for anything that you have as an effect of something that's deeper than your assumed horizon, that's captured in the input motions you're using for the analysis or in the reference hazard you are applying to that level. In reality, we should be using site response analysis to modify the selected ground motion prediction equation that we are using to characterize the reference ground motion. So when you have a GMPE, we have a site term, and here a GMPE for a reference condition that will define a condition from relative to which you conduct your site response analysis. Then the site term in that reference equation represents an average response of the entire data set, or the entire ground motion data set, average for the parameters that define your reference half space. So typically, we're talking about VS30 or Z1.0. And generally, if we can assume that this reference condition is linear, then our response is capturing the average network response, including the effects of crash of VS profile, the effect of damping, and kappa naught that correspond to that reference condition. When you are trying to predict hazard for a site-specific condition, then you need to modify this reference condition, and we modify this reference condition with what we are calling a site adjustment factor. And in this case, the site adjustment factor represents the relative site effect between the site-specific condition and the reference condition for the GMPE. And because what we are trying to capture with this are the effects of the shallow profile, the effects not just of the very shallow profile, but also the differences in the profile in depth with respect to the average condition for the GMPE. And if we have nonlinearity, we also are accounting for nonlinearity. So to compute site response, site adjustment factors, then we need to consider both the reference condition, and the site-specific condition. And in this respect, the site adjustment factor is accounting for the differences in the site-specific condition, both in terms of the shear wave velocity and damping effects, and the near-surface soil condition at the site. So we can do this in two ways. One, which will be a two-step approach, is we do first a correction for the deep velocity structure, and after doing that, we do a second step with the more traditional geotechnical site response approach, in which we correct for the shallow portion of the factor. And typically, the first correction is what was called a VS kappa correction factor. The second correction is our traditional site response analysis, by which we compute our amplification factor. An alternative approach, which is an approach that has been adopted already for several years in hazard projects, is to do this correction using a single-step approach, where we model an entire profile. Now we are talking about a scale that's much larger than the traditional geotechnical scale, but the entire profile, both for the host and for the target. And then we apply an input motion both to the same input motion to both the host and the target, and we compute the relative spectral accelerations. We take the ratio of both to compute our site adjustment factors. In this way, we are accounting in a single step both for the differences in the deep crustal profile and the difference in the shallow profile. What's important, however, is that we need to take into account what are the uncertainties in computing these factors. And to do this, we need to be able to differentiate what's epistemic and what's aleatory. And I don't need to go into details here because Professor Abrahamson already went into details. Aleatory being any uncertainty that's presumed to be intrinsic to a model and cannot be reduced with additional data, whereas epistemic uncertainty is the uncertainty that within the confines of our model can, at least in principle, be reduced with additional data. And separating these uncertainties is difficult. And in fact, the distinction cannot be made unless it is done within the confines of a model. That's why I like Norm's definition of modeled versus unmodeled uncertainty. It is, and this is from a paper from Professor Derkioregian, that it is the model builder responsibility to make the distinction between the two types of uncertainty. So in site response analysis, the distinction depends on how the site response is accounted for. If we have a generic site amplification term, such as an in-ground motion prediction equation, then we have a parametrization that's based on proxies for the site effects, which means that we are assuming that all the sites that share a similar proxy share also a similar behavior. So the aleatory variability then will include variability from station to station between stations that share those proxies. If we do site-specific analysis, then the site response analysis will be able to capture any repeatable effects that occur at that station. And the aleatory variability then, because you're already capturing the particular behavior of that station, the aleatory variability should not account for differences in spatial differences in amplification between stations. So if we put this in terms of the aleatory variability, we have what's called a total sigma that includes a site-to-site variability, whereas when we do site-specific amplification, that site-to-site variability isn't there, and we end up with a single station sigma. This is removing ergodicity only of one of the components that Professor Abrahamson mentioned in the talk earlier today. And the difference is important for two reasons. One, if we know what's epistemic in nature in our model, it's uncertainty that we can possibly reduce. And it's also important because of the way we account for it. We account aleatory variability in the hazard integral, results in changes in the slope, whereas the epistemic uncertainty will give us multiple hazard curves using an approach of logic tree, the logic tree approach that has been used traditionally. Okay. I'm not going to spend much time on this because Professor Abrahamson already mentioned this before, But when we have a single station sigma, we have a significant reduction in the uncertainty. And this can have high impact, especially for critical facilities, because in reducing the slope of the aleatory variability, we affect particularly ground motions at long return periods. Okay? But there is a cost. The cost is that because we are removing a component of the variability from the aleatory side, we need necessarily to account for the epistemic uncertainty, because we need to be able to estimate what is that repeatable component that we are removing from the aleatory variability. Mm-hmm. So really, the non-ergodic approach is a shift from aleatory variability to epistemic uncertainty. If we don't add information, our results shouldn't change. It's just the process by which we are accounting for the uncertainty is changing. However, if we have additional information, then our results will change. Okay, so the uncertainty, when we talk specifically about epistemic uncertainty inside response, then we need to consider uncertainties, first of all, in the reference condition, and the profile and the density, and in the small strain damping, which is accounted by the kappa parameter that essentially integrates damping across the entire profile. We need to consider uncertainties in the site-specific condition, that is, uncertainties in the VS profile, uncertainties in density profile, uncertainties in small strain damping, which again is accounted by the kappa knot parameter, and possibly is also constrained, especially for materials that are accessible to us or near-surface materials, from the type of laboratory test that Professor Stocky was talking about earlier. We need to account for uncertainties in the nonlinear behavior, modulus reduction and damping curve. Professor Stocky will tell you that we have uncertainties even when we are sampling or we're testing for a single specimen, we will have variability. We saw that with the basalt curves that Professor Stocky was showing. And also, we need to account for spatial variability within the site that we are analyzing. There is some inherent variability, and how we do how we capture this variability is in itself an uncertainty that we need to consider. And our profile is no longer a generic average profile, so there is uncertainty in the layering, potentially in structure, in 2D or 3D structure, etc. And an additional source of uncertainty is related to the model uncertainty, because we are doing a prediction now for these repeatable effects, and to do this prediction, we are doing some type of modeling, 1-2D modeling, and we need to account for the uncertainty in our analysis as well. Okay? So if I go now to the uncertainty in our target profile, to our site-specific profile, then how do we account for this? In a document that the NRC put out after the Fukushima earthquake, after the Tohoku earthquake, they propose, on this document propose or recommends to account for epistemic uncertainty using alternative base case profiles. And this means that we take our best estimated velocity profile, best estimated plus some uncertainty, minus some uncertainty, and we do the analysis. And you can easily build a case. This is a hypothetical case where you postulate this an upper, median, lower uncertainties, and you compute the amplification factors, and you will see that your amplification factors sometimes they collapse, and they collapse not because the epistemic uncertainty in the predictions is being reduced to zero. It's just an artifact of how we are postulating the uncertainty by simply scaling profiles up and down. Mm-hmm. So you cannot read this, but these three profiles at some frequencies would predict really no epistemic uncertainty for site response. We know that's not the case. We can avoid this by being more systematic in the way we capture the uncertainty. So by capturing the uncertainty in our profiles, using a full capture of the epistemic uncertainty, much in the same way that we do for ground motion models, by building a site response logic tree that accounts for all the sources of uncertainty. This is from a pilot study that was funded by the NRC. It's published in the Research Information Letter in 2021. This is for the Garner Valley downhole array site, where a logic tree is built capturing uncertainty in the analysis method. This is part of the analysis method, input parameters to the analysis method, in the VS profile, in the uncertainty, in modulus reduction, et cetera, et cetera. So you capture all the uncertainties, and then you do site response analysis for every branch of the terminal, every terminal branch, including randomization to capture aleatory variability. And then you can sample these uncertainties into a discrete number of site adjustment factors. And there are multiple advantages to this approach. Is one, and probably the nicest, is that the complexity of the site response logic tree doesn't penalize the hazard analysis, because it doesn't matter how complex is your site response logic tree, we can sample the results into a limited number of branches. 7 branches seems to be a good number to capture not just the median, but also the fractals in the resulting hazard. And you can do this to do essentially what's an elaborate sensitivity study, to be able to, you can use the logic tree to do an elaborate sensitivity study to look at what factors, what uncertainties are affecting the most site adjustment factors. For this sample study, again, you can look, for example, at the use of different modulus reduction and damping curves, how they result in different site adjustment factors, or you can do a variance contribution plot to see which elements of your logic tree are contributing the most to your uncertainty in site adjustment factors. I haven't mentioned model error yet. Again, our assumption is that we have typically we do 1D site response analysis, and there are multiple assumptions to the 1D response analysis that are not generally realized, so we need to account for model error. I will expand on this topic on one of the sessions tomorrow, so I will not mention much today, other than the fact that the model error right now is something that's not very well understood. There are different estimates. If you look at work that was done by John Stewart at UCLA, they have model error estimates that go up to about 0.3, 0.35 and over some frequency range. This is a value that's relatively high, or it's actually very high. If I have a student, Madhi Bahrampuri, who computed uncertainty using KickNet using surface and borehole arrays in the KickNet stations, and within a Bayesian framework. And depending on how much uncertainty we assign to our velocity profiles, we get either large model error if we assign low uncertainty to our measured velocity profiles, or we get relatively low model error if we assign relatively large uncertainty to the velocity profiles that we are starting. In reality, this value is probably somewhere in between the two red curves, exactly where I think more research is needed to understand that. So I'm going to talk in the last few minutes about implementations in recent projects. In general, site non-ergodicity now is implemented routinely in projects starting, and Norm, please correct me, I think it's the Pegasus project where this was started.
No. The first group that ran it was probably BC Hydro. They did it at Diablocan in 2009.
Okay. So I stand corrected. So BC Hydro first, Diablo Canyon. That's why it's always good to have Professor Abrahamson in the room. And the main driver is not, you are reducing uncertainty, you are reducing aleatory variability, which has an advantage, but the main driver is to avoid double counting uncertainty, because when we are making analytical estimates of the site term and we are including the uncertainty in our predictions, then if you do not remove the corresponding aleatory variability from the sigma, then you are double counting uncertainty. In Diablo Canyon is also a case where instead of using analytical studies, there were recordings at the site, so they attempted to constrain the linear portion of the site term with data. And it will be ideal that if we can always do that, you don't need that many recordings to get an advantage for constraining the site term with data. Then path non-ergodicity, and Norm already talked about this. We can use single path sigma, and as far as I know, and again, Professor Abrahamson can correct me, this was done in the Palos Verdes site, and I don't know if it was done in other nuclear projects as well. And this was possible because the source to site path was easily sampled because most of the earthquakes were coming from California, and that was the source that contributed the hazard. So that source to site path was well sampled. In future implementations, and this is again the talk that was given this morning by Professor Abrahamson, small magnitude data can possibly help capture spatially variable attenuation. This would be repeatable patterns. And there are models, non-ergodic models, and can be useful to constrain ranges of epistemic uncertainty in model coefficients. And this is already the talk that was given earlier today. The example I have here today is from the INL SHAC Level 3 project, and where we built a site response logic tree that accounted for epistemic uncertainty in our prediction of site effects due to multiple contributors. These contributors included our uncertainty in the shallow profile, shallow being defined as a component of the profile that we could measure either using surface wave or borehole measurements. Then the deeper profile that was used to account for the Krasov scale amplification, our kappa, which accounts for overall effects of damping, and modulus reduction and damping curves. So going systematically through these contributors, we start with a shallow profile. The data that we have available were measurements using MASW and microtremor array measurements, as well as, I should have said that, otherwise I'm going to get killed over the next of the week. We also had SASW measurements, which are stated here, but not here, that were done by Professor Stocky. And then we had borehole measurements, both downhole and PS logging at the site. In addition, I should mention that the study at INL had 5 different target locations, so we're looking at 5 sites that were located across the whole Idaho National Lab. We also had several geotechnical boreholes across each site, so we could develop a good stratigraphic profile and have an idea of how this stratigraphic profile varies across each one of the sites. Our philosophy in building the logic tree was to construct the shallow part of the VS profiles using independent surface wave measurements and to build the profile from our understanding of the site's lithology and model linking lithology to shear wave velocity using measurements of velocity that were obtained from borehole-based measurements. So there were no preference given to surface wave-based measurements and borehole-based measurements. I may have a heated discussion and argument about this in dinner tonight, I don't know. But our philosophy was that these 2 types of measurements are very different. Surface wave measurements capture a larger volume of soil, and 1D site response depends on a volume of soil around the control point. So in this sense, surface wave measurements are more consistent with the wave propagation phenomenon that is what we are trying to capture. On the other hand, borehole-based measurements, an advantage is that they capture details of vertical variation in soil properties, including more localized measurements of velocities in interbeds that were present in the INL site. The INL site is a volcanic site where you have layers of basalt and layers of interbeds of mostly alluvial and aeolic deposits. So these velocity differences are well captured by borehole-based velocity profiles. On the other hand, borehole-based measurements are just a point measure. So rather than measure a whole volume of soil, we are just measuring a point. And surface wave measurements on the negative side, they don't have, or they are not ideally suited to capture velocity reversals or possibly thin layers that exist in the profiles. Moreover, the inversion of a dispersion curve that's measured using surface wave measurements is non-unique. So we don't know exactly what velocity profiles we get, or we can get multiple velocity profiles for a single dispersion curve. So one other decision we made is that instead of trying to build a model of different velocity, or a single model out of all our surface wave measurements, we took independent measurements that were given to us by the experts that did the measurements and used profiles on these independent measurements, with the idea that rather than trying to construct an artificial shear wave velocity profile that puts together all the independent measurements, each measurement is really a representation of a dispersion curve, and you cannot decouple what's at near the surface with what's at depth. So in that sense, we had inversions that were done using love wave and Rayleigh wave velocity for the MASW-based models, and we had 4 different arrays at this particular site that represented the SASW measurements that were done by Professor Stocking. For the weights on these, which I don't indicate here, but the weights on these profiles were related to the confidence that we had on the profiles, the confidence of the developers of each profiles that they had on the validity of these profiles, and on how consistent the resulting profiles were with the measured dispersion curves. For borehole-based profiles, we had a constructed lithology using, and this is an example for one site, an extensive set of borehole measurements. You can see here some characteristics. These are interbeds, and some of these interbeds are relatively thick, as you can see these interbeds here, for 2 sites that actually on opposite, 2 boreholes that are on opposite locations across the site. So this will represent continuous interbeds, whereas these very thin interbeds are, while they are present all over the site, they are highly discontinuous. So we had a model where we didn't include the thin interbeds, another model where we included a model for these thin interbeds using a Poisson model. As mentioned before, we constructed the profile using the lithological profile, for which we had significant information, and then we assigned values of velocity, shear wave velocity, to different units within the profile from a regression that was done using velocity measurements across the entire Idaho National Lab. For our interbed model, and model for the thin interbeds, we used a Poisson model that was calibrated using the rate of interbeds that were observed at the site. We also had this is a typical profile on the site. You can see these interbeds. These interbeds, strangely, or maybe not strangely, at least it was a surprise to us, had a very strong impact by introducing a significant degree of attenuation across a broad range of frequencies. So we were a bit suspicious about how much attenuation these interbeds were introducing. Fortunately, so one alternative to this was to introduce some smoothing of the interbeds, which acknowledged that the wave propagation of these interbeds, the assumption of one-dimensionality for these interbeds, was overestimating the amount of energy dissipation. Unfortunately, we had measurements at some of the sites. In red here is, with limited data, an estimate of what is the transfer function that was obtained from measurements, and the other lines are 1D results of 1D site response analysis. The lower ones are ones where we take the measurements as is. The higher ones are estimates where we smooth out the presence of these interbeds, and we favor strongly then averaging across velocities across the interbeds to limit the amount of energy dissipation due to the presence of these interbeds. For the deep profile, we use borehole-based profiles in 2 deep boreholes that were present on the site, and we assign either one, the other, or both profiles on a logic tree format by depending on how close we were to these 2 boreholes across the site. We add uncertainty, in this case using 3 branches based on uncertainty on our an estimated Poisson's ratio for these boreholes. And also, we didn't always add this uncertainty. We made an evaluation of whether the uncertainty contributes or doesn't contribute to the epistemic uncertainty. As you can see, this is for one of the sites. The contribution to the epistemic uncertainty from using the 3 alternative deep boreholes, deep profiles, was very small, except at very low periods. This axis is missing periods. But even in these low periods, our uncertainty, it was within a range, our minimum epistemic uncertainty, so we eliminated in some cases this profile. And finally, we had kappa. And one important point to make here, that we had sites where we had instruments and we could measure records and make an estimate of kappa that was done through inversions. At these sites, we had much lower uncertainty on kappa. At sites where we did not have instrument, we had a higher uncertainty in kappa. And this is a big change to the high frequency hazard. Another reason to have measurements. Okay, and then we had modulus reduction and damping, and we had site-specific measurements at some sites, we didn't have it at other, and the weights reflected that in our final weighting. So I'm going to conclude rather with a summary of what I presented, with what concepts are transferable to non-nuclear projects. Because many of us work on non-nuclear projects, and I think one of the important lessons is that it's difficult to capture uncertainty when working in isolation. And the SHAC approach is a good approach to capture uncertainty. And then side effects are better captured when site response analyses are conducted both for the reference and for the site profile, because what our objective for the site response analysis is to correct for what the ground motion prediction equation is predicting. There is a nice paper, again, by Professor Abrahamson, Williams and Abrahamson, that addresses this and proposes that this is what needs to be done, not just for hazard projects, for projects for nuclear power plants, but in general. The concept of the logic tree helps to think about uncertainty in a systematic way. And then for site-specific approach, single station sigma makes sense. And it requires investment in properly capturing the uncertainty in site-specific amplification, and requires project-specific PSHA with single-station sigma reference hazard. Reference hazard that's conducted using single-station sigma. For general projects, that doesn't exist yet, but hopefully this is a direction that, at least in the US, the USGS is going to take to produce hazards using single-station sigma. I will conclude with this. Thank you very much. Okay.